Okay, so we're asked to describe fully the single transformation that maps triangle P onto triangle Q. Read these questions carefully. Triangle P is the larger one and triangle Q is the smaller one. Now, it should be pretty clear to see that triangle Q is half the size of triangle P. We still call this an enlargement. It's an enlargement, scale factor 1/2. And enlargements have to have a center of enlargement. This is easily found by tracking back with lines to see where those lines meet. And it's pretty obvious these lines are meeting at the origin. So we'd say center 0, 0. And that's the first part of my question done. Now the matrix that represents this transformation has to halve the x values and it has to halve the y values. So what happens to the x values goes in the first column. 1, 0 would now become 0.50. And 0, 1 would now become 0, 0.5. So that's the matrix that represents this transformation. Whatever the scale factor is for an enlargement, that's replacing the 1 and 0 in our basic 1, 0, 0, 1 identity matrix. So now we have another part of the question. We've got the point P with coordinates 1, minus 4, and we're asked to find TP. So TP is the matrix T applied to the vector pointing at the point P, which is obviously 1 minus 4. And I just do my matrix multiplication to find out the new vector. I'm getting 4 up here and 1 down here if I do my matrix multiplication. So the new point P is 4, 1. TUP, well, this means, paying attention to the order that I've been given, TUP is 0, minus 1, 1, 0, then U, 3, 1, 0, 2, and then P, 1, minus 4. You could multiply the matrices together first, or the matrix and the vector, and then the matrix and the new vector. That's how I'm going to do it because it's easiest. So I'm going to hang on to my 0, minus 1, 1, 0, and multiply together these two over here. That is 3 add minus 4, which is minus 1, and 0 add minus 8, which is obviously minus 8. Multiplying these together, I'm getting 8 for the top, and I'm getting minus 1 for the bottom. And so TUP is the point with coordinates 8, minus 1. Now I'm asked to describe the single transformation represented by the matrix T. Once again, if you've learned these, you can just write it down, or we can work it out as we go. Now we see in the first column of matrix T that the x vector, the 1, 0 vector, has been changed for a y vector 0, 1. So that means my 1, 0 vector is now up here, right? Maybe it's rotated up here, maybe it's reflected up here. We don't know until we look at the other side of it. My usual 0, 1 vector has become a minus 1, 0 vector. So the vector that usually lives over here now lives over here. And it looks pretty clear to me that this is a rotation. If we rotate the 1, 0 vector 90 degrees anti-clockwise, I end up with a 0, 1 vector. And if I rotate the 0, 1 vector 90 degrees anti-clockwise, I end up with this minus 1, 0 vector. So it's a rotation of 90 degrees anti-clockwise. As always for matrix transformations, around the point 0, 0. The matrices A and B are defined like so. I want to calculate A plus B and A times B. So A plus B is really very easy. All I'm going to do is add the corresponding elements. So 3 plus 0 is 3, 4 plus 2 is 6, 4 plus 2 down here is also 6, and 3 plus 0 is 3. A times B is done, well, the usual way. So if I multiply first row and first column, I'm going to get 8. First row and second column, I'm getting 6. Second row and first column, I'm getting 6. Second row and second column, I'm getting 8. Now we get something that looks quite complicated to show that a plus b minus ab is ki, where k is an integer, a whole number, and I is the 2 by 2 identity matrix. We need to know what this is. The 2 by 2 identity matrix is 1, 0, 0, 1. In terms of transformations, which we've seen a lot of in this worksheet, nothing is happening to that x vector and nothing is happening to that y vector. 1, 0 in the first column is still 1, 0, and 0, 1 in the second column is still 0, 1. So essentially the identity matrix is the one that doesn't do anything. So let's now look at this. I've already worked out a plus b, and I've already worked out a times b, so I'm going to start off by writing down that a plus b is 3, 6, 6, 3, taking away ab, which is 8, 6, 6, 8, and working out what that comes to. 3 minus 8 is minus 5, 6 minus 6 is 0, 6 minus 6 is 0, 3 minus 8 is minus 5 again. Well, this is pretty close to that 1, 0, 0, 1 matrix. It just has minus 5s instead of 1s. In fact, if we factorize out, which is not quite the right way of saying it, but it's good enough, if I factorize out that minus 5, I will be left with 1, 0, 0, 1. And so I have shown that a plus b minus a times b is some integer, in this case minus 5, times that identity matrix. And so I am done. The triangle DEF is obtained by applying to triangle ABC the transformation T represented by this matrix. Calculate the coordinates of D, E, and F. So, the most efficient way to do this, especially if it's an unfamiliar transformation matrix, as it is here, is to stick together the coordinates of your triangle, A, B, and C, in one big matrix and multiply them all together. So, what I mean by this is I want to do this matrix multiplied by a matrix containing the coordinates of A, B, and C. So A has coordinates 1, 1. B has coordinates what looks like 3, 1. And C has coordinates 3, 2. Okay, a quick look at these matrices will realize that we can multiply them together. 2 rows by 2 columns multiplied by 2 rows by 3 columns. The 2's in the middle match up. So let's do this multiplication. I'm going to end up with another 2 by 3 matrix. First row, first column, the 2, 2 times the 1, 1. So I've got 2 plus 2 is 4. Moving along to the next one in the first row, that's 2, 2 times 3, 1, which is 6 plus 2 is 8. 2, 2 times 3, 2 is 6 plus 4 is 10. Moving on to the second row, minus 2, 2 times 1, 1 is going to come out as 0. Minus 2 times 1, add 2 times 1 is 0. Minus 2 times 3, minus 6, add 2 makes minus 4. Minus 2 times minus 3 is minus 6. And 2 times 2 is 4. Add those together, we're getting minus 2. So if these were the coordinates of A, B, and C, these are going to be the images of A, B, and C. So I need to now plot 4, 0 for where A ends up going. So that is here, A dash. I need to plot 8 minus 4, and that's where B ends up. So 6, 7, 8, and then down to minus 4, which is here, I believe, if I've got my scale right. That's where B ends up. And C ends up at 10 minus 2. So 10 minus 2, I believe I've got that right if I put it here. And I would connect these up with a ruler, obviously, to make the new triangle, and they're calling that D, E, and F. So I'll say D, E, and F there. So we can see this is not a simple transformation at all. The shape's distorted and changed up in all sorts of interesting ways. So I've calculated the coordinates of D, E, and F. D is the 4, 0. E is the 8 minus 4. And F is the 10 minus 2. And I've drawn that on the diagram. T is a combination of an enlargement and a rotation. I want to find the scale factor of the enlargement, and I want to find the magnitude of the angle of the rotation. Okay, so if I look now at what's gone on, and I examine where the right angle ended up, it ended up down here. I think it's pretty clear that that rotation would be something along the lines of 45 degrees-ish. If I want to know what the scale factor of the enlargement is, I want to compare the lengths of the sides. Now, this grid has been drawn very carefully and very much to scale. So if I've got a ruler and if I've got a protractor, I can do that very easily. So if you measure this length and measure this length, divide them, you'll get the scale factor. If you take a protractor and you maybe extend this line over here, you can measure the angle in between there. And that's how I would do that last part of the question. If you are getting close to something like 45 degrees, or close to, say, a scale factor of 2, remember this is supposed to be exact, right? So that would be the guide you'd go on. Certainly it looks like a scale factor of 2 should be present, but measure and just be careful. And that concludes our answers to this worksheet.